You've had this experience, your application is running fine, traffic is normal, nothing has been deployed, and then, quietly, your response times start climbing. Not spiking, climbing, steadily. At 2 a.m. on a Tuesday, you check your code, nothing changed. You check your database, healthy. You check your traffic, normal. You file a support ticket. The provider investigates and finds nothing wrong, because from their perspective, nothing is wrong. Your instance is running, your resources are allocated, your isolation boundaries are intact, but your application is still slower. What you've just experienced has a name. It's called the noisy neighbour problem, and the reason it's so persistently difficult to diagnose is that it doesn't live in your application, your configuration, or your provider's infrastructure. It lives in the gap between them, in the shared physical hardware, underneath the isolation boundary everyone assumes is protecting you. Understanding it changes how you think about cloud performance forever. When you provision a virtual machine on any cloud provider, you're told your environment is isolated, and that's true, up to a point. The hypervisor allocates you a specific slice of memory. You cannot read another tenant's memory. That boundary is real, and it holds. But isolation is not the same as exclusivity. Your virtual machine is running on a physical host, a real server in a real data center, with a real CPU, real network cards, and real storage controllers. That hardware is shared, not just between you and one other tenant, between dozens of virtual machines simultaneously, and some of the most performance-critical resources on that hardware cannot be partitioned the same way memory can. They are shared pools. Everyone draws from them at the same time. There is no quota, there is no fence. Think of it like a block of flats with its own water meter per flat, but a single shared boiler. Your flat's water supply is yours. But if your neighbour takes a 20-minute shower, the water pressure in your flat drops. Your pipes are yours. The boiler is shared. The isolation was real, and the interference happened anyway. The wall is real. The pipes behind it are shared. There are 3 resources where this matters most, and each one fails in a different way. The first is the CPU cache. When your code runs, the data it accesses most frequently gets pulled into the CPU cache, a tiny, extremely fast bank of memory sitting directly on the chip. A cache hit takes around 4 nanoseconds, finding data there. A cache miss takes around 100 nanoseconds, having to fetch from main memory instead. That difference multiplied across millions of operations per second is the difference between a fast application and a slow one. The CPU cache is not partitioned between tenants. It is physically shared by every process running on that chip. When a neighbour's workload runs, a batch job, a machine learning training run, a nightly ETL process, it loads its own data into the cache, evicting yours. Your code starts missing. Every miss costs 100 nanoseconds instead of 4. Your latency climbs, with no visible cause in any metric you're watching. This has a name, CPU steal. It's the percentage of time your virtual CPU wanted to execute but couldn't, because the physical CPU was busy with something else. On a lightly loaded host, it's near 0. On an oversubscribed host with a busy neighbour, it can climb to 10, 15, 20%. You can see it in the top command on Linux, right now, on any running instance. Most engineers have never looked. The second is network bandwidth. The physical network card connecting your host to the data center fabric has a fixed capacity, typically 10 or 25 gigabits per second. Every virtual machine on that host shares it. The hypervisor manages the queue. It cannot manufacture bandwidth that isn't there. When a neighbor saturates that card, a large data transfer, a backup job, a deployment pulling container images, everyone else's packets queue behind theirs. The result isn't dropped packets, it's jitter. Variability in how long packets take to arrive. Your P99 latency climbs. Your SLOs start blinking. Your application looks degraded. The network is fine. The shared pipe is full. The third is disk I/O. The storage controller servicing your instance processes read and write requests in sequence. When a neighbor sends a burst of writes, a database checkpoint, a log rotation, a batch insert, your reads queue behind their writes. Disk read latency spikes. If your application is database heavy or relies on local disk, this shows up immediately. The disk is fine, the queue is backed up. 3 different resources, 3 different failure signatures. One common cause, a shared physical pool, with no per-tenant quota, underneath an isolation boundary that was never designed to protect you from this. Here's why this class of problem is so persistently misdiagnosed. Standard application monitoring watches effects, response times, error rates, throughput, queue depth. When those metrics degrade, you look at your application because that's where your monitoring points. You look at your code, your database queries, your memory usage. All of them are fine. The incident closes as inconclusive. It happens again 3 weeks later. What you need is infrastructure-level metrics, the layer below your application, at the physical host. CPU steal tells you whether the physical CPU was available when your virtual CPU needed it. Network jitter, at the hypervisor level, tells you whether shared bandwidth was saturated. Disk I/O wait time tells you whether the storage controller was backed up. These metrics don't live in your application's APM dashboard. They live in the OS. CPU steal is in top and VM stat. Disk I/O wait is in IO stat. Network jitter requires packet-level measurement. None of them are turned on by default in most monitoring configurations. None of them are the first thing an engineer looks at when a ticket comes in. This creates a consistent pattern. Noisy neighbor incidents get diagnosed as application bugs. Because the shared physical host is still shared, application-level monitoring shows you effects. Infrastructure-level monitoring shows you causes. The noisy neighbor lives entirely in the gap between those two views. Cloud providers are not blind to this problem. They invest heavily in mitigating it. Oversubscribed hosts with degraded performance are bad for everyone, including the provider. The primary mitigation is placement management. Providers monitor host-level utilization and spread workloads to avoid consistent oversubscription. This works at the population level. It reduces the frequency of noisy neighbor incidents. It doesn't eliminate the underlying physics. For workloads where performance predictability genuinely matters. Financial systems, real-time APIs, latency-sensitive user-facing services. Providers offer a different class of options. Dedicated instances and dedicated hosts on AWS place your workload on physical hardware, not shared with other customers. You eliminate external noisy neighbors entirely. Your own workloads can still interfere with each other, but the interference source is at least visible and under your control. Enhanced networking options like SRIOV on AWS and accelerated networking on Azure give virtual machines more direct access to physical network hardware, reducing the contention layer for network I/O. Provisioned I/O piece on storage volumes buys you a guaranteed number of disk operations per second, removing you from the shared I/O queue for that layer. The pattern is identical across every resource type. The default is shared, managed, best effort. The premium option is a guaranteed floor. The economic choice of whether that floor is worth paying for is yours. But it can only be a real choice if you understand that the default is a shared pool, not a partition. The noisy neighbor problem is not a bug. It's not a misconfiguration. It's not a failure of isolation in the traditional sense. The boundary between your workload and your neighbors is intact. It works exactly as designed. The issue is that the boundary was never designed to protect against shared physical resources. It was designed to protect against direct access. Those are two different things. And in cloud computing, only one of them is fully under anyone's control. The engineers who understand this distinction don't get surprised by 2 AM latency graphs with no visible cause. They know what to look for, where to look, and what it means when they find it. More importantly, they know when paying for a guaranteed floor is worth it, and when a shared pool is good enough. That's not a vendor decision, that's an engineering one, and it starts with knowing the difference between a wall and a pipe.